Hello friends, I am Professor Nisar Ahmed Khan from Department of Economics, Aligarh Muslim University. I'll talk about the population regression function, sample regression function, and the methods of estimating the model which we have specified. Now let us start with the population regression line or population regression function. So population regression function is basically, here we have one dependent variable and one independent variable, that is we are talking with reference to two variable model, and we have already told you about the dependent and independent variable. So in the population regression function, what we do, that we find out the average value of the dependent variable that can be associated with the given values of independent variable. So the values of independent variables are given, they are not going to change. We have to find which value of the dependent variable can be associated with the independent variable. And then we have the mean, we take the mean as mean of the dependent variable which can be associated with the independent variable. Now, what is the rationale of associating the mean value of dependent variable with the independent variable? Now, here one thing I would like to clarify, that mean here means conditional mean, because there are so many dependent variable. So which of these dependent variable can be associated with the independent variable? There will be only one. Let me tell you, suppose we have a function like this, y is a function of x, and we have plotted on a graph like this, and we have y here and x here. This is the given value of x, and we see this is the line. So with this one value of independent variable, there will be only one value of dependent variable. But if there are several values of dependent variable that are associated with this one value of independent variable, the question arises, which of these can be taken as the value of the dependent variable which we can associate with independent variable. Then all these values of the dependent variable, they have equal chance of being associated with the independent variable. So we find out the probability of all these dependent variable to be associated with independent variable, and this probability is multiplied by the values of the dependent variable, and when we do that, we find out the expected value of dependent variable associated with the given value of independent variable, and that expected value of dependent variable is now called as conditional mean. This is different from the mean that we usually say, that is arithmetic mean, because in the arithmetic mean all the values are certain to happen, that is, there is a certainty about their happening, there is no probability there, so we can just add them and divide by the number and get the mean. But here there is a probability associated with the values of the variable, so we, instead of finding the arithmetic mean, we find conditional mean. So in the population regression function, what we see, that we have to find the conditional mean of the dependent variable which is associated with the independent variable. The population regression line shows the relationship between the two. That is, it shows the conditional mean of the dependent variable, relationship between conditional mean of the dependent variable and the given values of independent variable. Now, we have an example. In our example, we take a hypothetical country, and in this hypothetical country, there are 60 households. Now, there are two ways of studying the relationship between income and saving. We want to study. One is that we can conduct a census inquiry, that is, no unit in the population is left. Another way is to conduct a sample inquiry. But we start with the census inquiry, that is, the entire population is going to be covered and no unit or no household is going to be left. So we have taken a hypothetical economy, and in this hypothetical economy there are 60 families. So we have the income of 60 families and we have the savings of 60 families. The income of 60 families are given in 100, that is 200, 400, 600, 800, 10, and the savings are given here 60, 65, 70, 75, 80. Now, when data is collected, then this data has to be expressed in this particular form. How it is done? That we first of all find out what can be the different income level so that all the households are covered. If one household is covered in one, associated with one income level, other may be associated with another income level. So all the households should be covered. So we saw that if you take the income level, these are the 10 income levels, and if you take these 10 income levels, then all the household will be covered and no household would be left. So we have the income of the household, we have the saving of the household. The first thing that we have to do, that we have to find the conditional mean of the dependent variable. Here the dependent variable is saving. Here saving is a function of income. S is saving and Y is income. So we have to find out the conditional mean of saving that can be associated with this. This we write like this. We can write it like this. That is, here we are denoting the income by X and saving by Y. So we can use the same notation instead of S. So we say it as, that is, Y is a function of X. So X stands for income and Y stands for saving here. And if this is so, then it means we have to find the conditional mean of Y that can be associated with this given value of X. For example, one given value of X is 200 and we have to find out the conditional mean of Y that can be associated with this. So here there are 1, 2, 3, 4, 5 values, and all these have equal chance of being associated with this independent variable. So the probability of one value being associated with the independent variable is 1 upon 5. 1 upon 5, we multiply this by all these values by their respective probabilities and we add. So we can find out, we will write here, we can find out here expected value of Y given X1. X1 is, this one is X1, this is the X1, and we want to find out the expected value of Y given the value of X1. It will be equal to 1 upon 5 multiplied by 60 plus 1 upon 5 multiplied by 65 plus 1 upon 5 multiplied by 70 plus 1 upon 5 multiplied by 75 and plus again 1 upon 5 multiplied by 80. If we carry out this, then we will get this 70. So 70 is the mean, conditional mean of Y that is associated with X1. So expected value of Y given X1 is equal to 70. This is how we can find the conditional mean of Y associated with X2, that is this one, conditional mean of Y associated with X3, X4, X5, X6, X7, X8, x9 and x10. So if we calculate that, we will get here the means are calculated, conditional mean. These are the conditional means that are already calculated here using the technique that I told you. Yes, these are the conditional means. Expected value of y given the values of x. This is the same table that we just saw. Now this table is being plotted here. Here we have the values of x, that is this one, the values of x we have here, and the values of y we have mentioned here. So here we have x, here we have the values of x, and here the values of y. Now with this value there are 5 values that are associated, and similarly with this 2, 3, 4, 5, 6. There are 6 values that are associated with this. Like this we have this, and we have found the conditional mean of y associated with a value of x, and these conditional means are joined together and we get this line which we call as population regression function. So this is our population regression line or population regression function, whatever you can say. So population regression function means finding the conditional mean of dependent variable which is associated with values of independent variable. The rationale for associating the conditional mean with the given values of independent variable I have already given you. Now this is the same thing, expected value of y is related with this x, that all this we have told you. Now this we have, it means y, expected value of y given the value of x, it can be written as alpha plus beta x. Now let me take you back to show this. This is the population regression function or population regression line, and if you join it here, this will be the intercept and this one is the slope of the line. So there are the equation of this line can be written as like this. Is equal to alpha plus beta x. This is the equation of this line. But we want to associate these values also because these are the deviation from the conditional mean. So, and these may be, if we consider that this is the saving that is associated with income, it means this deviation in saving from the conditional mean may be because of a number of reasons. One reason I have told you, because of the other variables whom you have assumed as constant, but actually they are not constant, they are changing. There may be measurement error and there may also be specification, and the influence of all this can be expressed by a random term, and if we do that, then we can write the actual values of y can be expressed as expected value of y given x as plus u. Now u takes into account the influence of all other variables like this, which are deviating from, take into account the influence of all other variables which are excluded from the model, plus it takes into account the measurement error or specification error. So you explain this, the difference between this and this is u1, and the difference between this and this is also u1. You can take it u1, u2 like this. So this is in terms of the actual values of y. This equation is in terms of expected value of y given the value of x. Same thing we have written here, that is this one, that this is the in terms of actual value of y, and this is, if we replace this one, then this will be beta 0, beta 1, xi, ui. We have written alpha and beta, but here beta 0, beta 1, and you have y, ui, yi minus xi. That is there. you can take difference between this ui is equal to yi is equal to expected value of this is the same thing. So this has two components. This is the component which is deterministic, which is explained, and this is the component which is the random component. We call it as this is unexplained. So this part is explained because our line explain this. For example, if we further take you back, then this line explain that so this with this value of y, this is the this value of x, this is the value of y. But these values are not explained, and these are explained, these are included u. So you take into account these values, and consequently we say that this is the unexplained portion, and we call it as non-systematic change. So the total change in y is divided into two parts. This is the systematic change because it follows a particular system. Systematic change is that change which follows a particular system, and consequently it is expressed by a line. So it means a system is being followed. So this is a systematic change, and this one is a random change. That is, this is a non-systematic change. So this is the systematic and this is the non-systematic part. We can also call it as fixed component because it is explained by the line, and this one is the random component. Now, the regression function, that is, if you don't want to conduct a population inquiry, or if you don't want to conduct a census inquiry covering all, because that may be quite costly, that may also be time taking. So what we usually do in economics as well as in statistics and econometrics, that instead of studying the entire population, we draw a sample and we carry out estimation from the sample, and then we have to test it how far we can rely on these estimates obtained from the sample. That is, how close these sample estimates are to the population parameters, because ultimate aim is to find out the population parameter, the values of the population parameter. But we are doing it in a different way by drawing a sample and estimating, and then we have to test, that is, how reliability of these estimates. So this is the sample regression function. This is the what we have done. This is the sample regression function, and this sample regression function is, that is, this is the estimated value of y, this is the estimated value of beta 0, estimated value of beta 1. This we will tell you in a moment. If we take, this is the entire population, that is all the 60 households. From this we will take a sample. We can take any sample, that is, we can, these values are fixed as far, these values are fixed as far as income levels are, these are fixed, these are not going to change. Now we can select any of these values and associate it with this. So in the sample we have one value of independent variable and one value of dependent variable. Not so many, because we are conducting a sample inquiry, not a census inquiry. So here we have we have taken two samples, we have drawn two samples. This is the one sample. You see the independent variable has the same values here as well as here, and it is same as it is in the case of population regression function. Now this is one value, this here we have this associated with this another value. Now these two are plotted here. These two lines are plotted here. What actually we do, that when we will actually plot this on a graph, taking saving on this axis, income, we will get scatter values, and through these scatter values we have to fit a line or curve. What is the rationale of fitting line or curve? That I'll tell you in a moment. But this is the sample regression function, and we are the two sample. Now once this is this one, if you join it here, it will give you the intercept, and this is the slope. Now we want to know, we already have population regression function, and we have the population parameters. Now once we estimate for the sample coefficient, we want to know how much these estimated coefficients are closer to the population parameters that we can know only through testing or applying various tests and constructing confidence interval. So what we have done here we have put the population regression function and sample regression function together. This is the population regression function, this is the sample regression function. This is just for the sake of comparison, so that the concept regarding the population regression function and sample regression function is crystal clear. Now this is the population regression function. So this one beta 1 beta 2 xi, that is conditional mean of y associated with the value of x, this is the systematic part in the population regression function. Now this is the actual value of y that is associated with this value of x, actual value. If this is the actual value, then this will be the u. The difference between this and this will be the ui. That is what we write this population regression function. We have written it, y is equal to let us use the same notation, that is beta 1 plus beta 2 x. This is yi, this is xi. I am not writing yi, xi just to save time, and so when I write y, it means yi. When I write x, it means xi. I will not be writing yi and xi, but here I have written it. So this plus ui. So this portion is this one, this is the explained portion, and this is the unexplained portion. This is the fixed systematic part, and this is the non-systematic part as far as population regression function is concerned. Then we have, this is the sample regression function, and in the sample regression function, this is the part which is the systematic part. This is the systematic part which is explained by the line, and this one is non-systematic part, this one. So the sample regression function we can write like yi is equal to, it is beta 1 hat plus beta 2 hat xi plus ui hat, that is estimated value of this here by the sample regression function. So this much is explained by the line, and this is not explained by the line. So this diagram clearly shows the both population regression function and sample regression function, and tells what is this. These are the population parameters, and we have to estimate beta 1 and beta 2, and these are being estimated from the sample regression function. This is beta 1 hat is an estimator for beta 1, beta 2 hat is an estimator for beta 2, and this ui hat is an estimate of ui. So now we come to this, because I told you that we are not going to conduct a population inquiry or a census inquiry. What we are going to do, and that is usually done in economics, that we take a sample, and from that sample is estimated, and that after estimating we try to find out how reliable these estimates are. So once we have collected the data regarding our dependent variable y and independent variable x, and we plot this data on a graph, then we get this type of scatter points. Now through these scatter points, we have to fit a line or curve as seeing the pattern of data. Observing the pattern of data, and we may have information from the economic theory that may also hint whether the relation between y and x will be a linear one, shows by line, or the relation between y and x will be non-linear, shown by a curve. So anyhow, we have to fit a line or curve. The question is, why do you want to fit a line or curve? What is the rationale for that? The rationale for this is that if we take this one, that y is a function of x, now it means that the relationship between y and x when other variables are constant, other variables are not changing, but actually other variables are continuously changing, and what we are observing is as far as y is concerned, it doesn't only contain the influence of x, but it contains the influence of other variables which are not part of the model, which have not been included, and consequently we see, but the relationship with one value of x, we have many values of y, several values of y. That is, you see that what we want to find out, with one value of x, only one value of y. What is this? Because this represents the true relation. I'll give you an example to explain this. Suppose there are two friends, one is y, another is x. We want to estimate the relationship between the two by assuming that all other variables which may affect their friendship are constant. If all other variables which are assumed as constant and they remain constant, which are going to affect their friendship, then their friendship will remain as it is. That is, that there will be, you will find a systematic relation between y and x. Whatever is the relation today, the same will be the relation tomorrow, same will be the relation day after tomorrow, and that relationship will be a systematic one, because all variables which may influence their friendship are being assumed as constant. So a true relation is always systematic, and the systematic relationship can be expressed either by line or by curve, because systematic means it follows a particular system, so we have a line or curve. So therefore, that is the rationale for fitting a line or curve. Now this true relation between y and x, that where we have assumed other variables which may influence their relationship, which may affect their friendship, are assumed as constant, but in actual practice they are not constant, and as a result we see that in non-systematic relation between y and x, that is, we see that they are friends, but when y is in trouble, x doesn't help. So it may be because of the influence of other variables, their friendship is not like it was earlier. But if we assume other variable as constant, then their friendship will be same. That is, it will be a systematic one. There will be a system, there will be a pattern as far as if y is in trouble, how x will react. X will certainly come to the help of y because their friendship is not affected by other variable. So that is the rationale for fitting a line or curve through these scatter points. Now the question is how to fit the line or curve. Suppose we take the line only. We don't take the curve, we take a line only. What is the how to fit a line? So fitting the line means that we have to fit the line so that all these points are covered, and because the difference between this point and line is an error, because technically we see this line should pass through all these points, but if line is going to pass through all these points, then it will neither be, it will show a non-systematic relation between y and x, but we want a systematic relationship which is shown either by line or curve. So the difference between this point and the line is called as error. We have to minimize this error as much as possible. Now, minimizing the error means, we can say that minimizing the error means that summation E should be as small as possible. But let us consider an example. Let us consider an example like this, where we have, suppose we write here that this is y, this is x. We have 3 points only. Instead of many points, we have only 3 points. And we fit a line through this, like this. The distance from here to here is, suppose, 1. Forget about sign, the distance from here to here is also 1, or let us put the sign plus 1. This one is also plus 1. And the distance from here to here is minus 2. So the distance between this point and the line is plus 1, the distance between this point and line is also plus 1, and the distance between this point and line is minus 2. So if we take the summation E, it will be 0. So we will not be able to minimize the sum of the error. This is called error. We told you E stand for the error. We are not able to minimize the error. So what we can do, and this is becoming 0, that the positive errors are cancelling the negative error. So we can take the minimize the mod value of the error. That is, we forget about the sign, take the mod value. And if we take the mod value here, then it will be 1, 1 and 2. It will be 3. But instead of that, if suppose I fit a line through these 2 points, this is another line, this is line A that we have fitted, this is the line B that we are fitting, and this line is going to, these 2 points are going to fall on the line. The third point is completely ignored. So the distance here from here to here will be now 3. This distance, let me remove this. Let me give you another diagram that will be, so we have 1 point, this is another, this is another. So we have fitted this line, this is, you can say plus 1, this is also plus 1, and suppose this line little bit far, so that it shows that the distance is more. So this distance is minus 2. So this is our line A. If we fit a line passing through these 2 points like this, and we call this line B, so the distance of this point, these 2 points are now falling on the line, so error with respect to them is 0. There is no error, there is no deviation, but at this point is the error will be now this one, from here to here, it will be minus 3. So minus 3 means that the error here will be minus 3. In this case, the error is only minus 3, and the earlier one also minus. So the both lines are, giving the same error here in this case. So the question is, which line is the best fit? If we take another example, suppose we take another example to express this more clearly. Suppose we take 1 point here, 1 point here, and 1 point here, and we fit a line through this, and the distance from here to here is plus 1, and distance from here to here is plus 1, and this distance is also plus 1. So if we take the mod value, it will be 3. And if suppose we pass the line through these 2 points like this, then the distance here will become, sorry, this is not plus 2, this is minus 1, sorry. So this distance will become minus 2 with this, because these 2 points are already on the line, this distance is minus 2. So we'll see that if we talk with respect, this is with respect to A, and this line is B. So with respect to A, the mod value of the total value of error is 3, and if we take the line this, then the mod value of the error here will be, what will be the mod value of error? It is only 2. So what we will do, that we will say the line B is best fit, because the total error here is only 2, whereas if we take the line A, the total error, the mod value of the total error is 3. But our common sense says that line A is a better fit, because it is giving due importance to these 3.1, 2 and 3, whereas this B is giving only importance to these 2 points and completely ignoring the third point, though the error is. So this criteria of minimizing the mod value of error is quite misleading. It may not give good fit. Then there is another way of tackling the sign, and that is, instead of minimizing the mod value of error, we can minimize the squared value of the error. We can take square value of the error. Now, if we take the square value of error in case of A, this is the line A, if we square, that is all the errors are squared, so that the sign problem is tackled. There is no problem of sign. So, if we square 1, this will be 1. If we square this one, this will also be 1. And if we square this as 1, so we'll see that if all these errors are squared, then we will have, that is, 1 square plus 1 square plus 1 square. So, it will be 3. This will be 3. But if we take this one here, if we take this one, then this is the distance, and that is in case of B, if we take the sum of squared error, then it will be 4. Because it is 2, the square of 2, it will be 4. Whereas here, because with reference to this, there is no error at all, and there is only one error, that is with reference to this point, and it is minus 2. So, if we square it, it will become 4. So, error here is 4. With this line, the error is 4, and with this line, error is only 3. So, it means when we are minimizing the sum of the squared error, that is more appropriate method, and that is we are going to take up that line which makes the sum of the squared error least or minimum. Now, this is what we call as least square method. So, this is the ordinary least square method. There are a number of other methods as well to carry out the estimation. One is maximum likelihood method, another is moment method. Now, this least square method was introduced by a German mathematician, Friedrich Gauss, and we have already told you about this method, least square method. Now, we will try to find out the ordinary least square estimator. So, this is the method of finding the ordinary least square estimator is given here. We have a very shortcut method of finding the ordinary least square method that I will tell you also. So, this is our population regression function. Let us change the notation. We have y alpha plus beta x plus u. This is the population regression function, and this is the sample regression function, where we have alpha hat plus beta hat x plus e. This is the sample residual, that is the estimate of u, that is this is the population disturbance term. This we can say as sample disturbance term, if you like. So, we want to find out this alpha hat is an estimator of alpha, beta hat is an estimator for beta. We have to find an expression for alpha hat as well as beta hat. That is what we have to find. So, how we can do it? Let us take this one, the sample one. We take alpha hat plus beta hat x plus e. Take the sum over all observations. So, this will become summation y, this will become n alpha hat, and this will become beta hat summation x plus summation e. Now, summation e will be 0. If you divide all the terms by n, this will become y bar, this will become alpha hat, because all the terms are divided by n. So, and this will become beta hat x bar. So, if we take the difference between this and this, that is, we take y minus y bar, that is this equation minus this one, then alpha hat here and alpha hat will get cancelled. We have beta hat x here, and we have beta hat x bar, and we have e. So, it will be beta hat x minus x bar plus e. So, if you denote this by small y, and if you denote by small x, then this can be written as y is equal to beta hat small x plus e. Now this e can be expressed as small y minus beta hat small x. So summation e square, that is we square these values and take the sum. Summation e square will be summation, in the bracket we have small y minus beta hat small x and raised to power 2. Now we have to minimize this. So for minimizing this, how to minimize this? Because what we have done actually by this, we have eliminated alpha. So this, if we take this is the sample regression function, taking y on this axis and x on this axis. What we have done, we have taken the mean of y, this is y bar and this is the x bar. So we are considering the line from here onward, that is from the average, and we know that in regression the coefficients are independent of the change in origin and scale. So if you change the origin from here to here, the line origin, it will not make any difference, line is same. So we can find out the slope of this line, even changing will not, that is we are taking advantage of that. So we'll minimize this summation e square with respect to beta hat. So let us differentiate summation e square with respect to beta hat and equate it to 0. So when you will do that, we will get minus 2 summation small y minus beta hat small x and x as equal to 0. This is what you will get. So if we open this, this will be minus 2 summation xy, because this x will be multiplied by this, and plus this will become plus beta hat summation x square, and this will be equal to 0. So if we can remove 2 now, we can directly write what will be beta hat. There are some steps that you can do yourself. It will be equal to summation xy divided by let us write it in different way because it has exceeded this. So we write it beta hat is equal to summation small xy divided by summation small x square. So this is the expression for beta. Here x and y are expressed in deviation form. X is x minus x bar, small y is y minus y bar. Now you must differentiate between the small y and capital Y and small x and capital Y. While capital Y and x are the actual values of y and x, the small y and small x are expressed in deviation form. So there is a difference between these two, small x and capital X. So here all the values of x and y are expressed in deviation form. This is a very simple formula for calculating beta hat. Once you have calculated beta hat and you already know y bar and x bar, you can substitute the value of beta hat here and you can also get alpha hat. So what will be alpha hat here? Alpha hat will be equal to, you can find alpha hat will be equal to y bar minus beta hat x bar. So you know y bar, you know x bar, you have already estimated beta hat, you can find alpha hat very easy. This is very simple method of finding, and this one is also easy to remember. Otherwise the two normal equations that we are getting, that the expression that we will have beta hat, it is same expression, there is no difference at all, but this one is easier to remember. That's why I also mention it additionally. So this is these are the two normal equation, and this is how we are doing it, and ultimately we get this beta on hat. It is same that this beta that we have got, there is no difference at all between these two. These two are same.